Here's an example of an application of what we've learned and another piece as well. If you were asked to find the slope and the concavity of this parametrically defined graph at the point 2, 3, our slope would be dy dt over dx dt. And so when I think about dy dt, I'm going to take the derivative of this equation for y. And so I will have 1/4 times the derivative of t squared, which is 2t, minus 1/4 the derivative of 4, which is 0. So we're really just going to have 1/4 over 2t, which simplifies to t over 2. And the denominator will be the derivative of the x equation. So we'll have 1/2. The derivative of t to the 1/2 will be t to the negative 1/2. So that t is going to show up in the denominator. That's square root of t. And so when I plug in my point 2, 3, where do I plug it? Notice both of these are in terms of t, but they gave me this point 2, 3 for a reason, so how am I going to use it? Well, I can look at x. X is equal to the square root of t, but we know that x is 2. And so 2 is really equal to the square root of t. If I square both sides, I can see that t equals 4. Just to make sure, let's plug in 4 here. When I plug 4 into the upper equation, 4 squared is 16. 16 minus 4 is 12, and 12 divided by 4 is 3. So that gives us the y-coordinate that we know we should have. So we know t is 4. That means our slope will be 4 over 2 over 1 over 2 times the square root of 4. Simplifying this, we're going to have 2 in the numerator over 1 over 2 times 2, or 4 in the denominator. That's going to be 8. So my slope is 8 at that point 2, 3. So we still need to find the concavity, and concavity, we can be reminded, in AB calculus comes from the second derivative of a function. It's the same with parametrics. So we need to figure out how are we going to find the second derivative of y with respect to x twice. And so the way this is written helps us that we are going to take the derivative with respect to t of our slope, which was dy dx, and we're going to put this over dx dt. And so notice there is a dx dt buried in this dy dx term, and so this is where we get our 2 dx dt's that this equation is implying, but we do need to take the second derivative of y. So that's going to happen twice. So in our case, we had dy dx equal to t over 2 over 1 over 2 square root of t. We're going to simplify this a little bit so that we can take its derivative more easily. So this is really t over 2 times the reciprocal, 2, times the square root of t all over 1. And as we see here, our 2's will cancel out. And when we multiply t times t to the 1/2, our dy dx is really t to the 3/2 power. So that is what is ending up right here in our formula. So our formula is telling us I need to take the derivative with respect to time of dy dx, and we just found dy dx was t to the 3/2. And that's going to be over dx dt, and dx dt was always this 1 over 2 square root of t. So I'm going to use the power rule to take the derivative of t to the 3/2. That will be 3/2 times t to the, subtract 1 from that power, 1/2, over 1 over 2 square root of t. Well, we'll simplify this a little further. 3 over 2 square root of t times the reciprocal, 2 square root of t over 1. We can see that the 2's will cancel out. I'm not sure why I keep writing 2 in here for this t. This gives me 3 times the square root of t times the square root of t is the square root of t squared, or just t. So our second derivative is 3 times t, and our time was 4. We found that previously. So when I plug 4 in here, I have a second derivative of 12, which is greater than 0, suggesting that we are concave up. We already had a slope of 8, so as you think of this, it's very steeply going up. This would be the path that we would have at t equals 4, and at the point x is 2, y is 3.